My name is Hans-Jürgen Meyer, and I have the pleasure to chair this second morning session. We have three very interesting talks that I'm really looking forward to, and my job is to stay on time, so I will very, very briefly introduce our first speaker. He's from ThermHex Waben GmbH. His name is Dr. Pflug, and he will tell us why Organosandwich panels are really an interesting approach to use. Stage is yours, please.
Thank you very much. Thank you. Yeah, ladies and gentlemen, oops, that was too fast. I would like to present you our Organosandwich panels. I'm Dr. Pflug from the ThermHex Waben GmbH, and it's a project or a product from EconCore ThermHex, and I will show you how cost efficient and sustainability can go together with these sandwich materials. Well, if we look to nature, then we see many examples of structured materials because nature is also very cost conscious and very resource conscious and uses minimum amount of material, and the honeycomb structure in the bee comb is well known for minimum amount of material used. And also in the history of transportation, there are examples like the first trains, which had a sandwich frame, and the first, self-carrying wing modern aircraft from Hugo Junkers had a sandwich wing, a big, thick wing for the first time, which used also corrugated structures because he could not bond the honeycombs to the skin as we can do this today. So, but even early in transportation, innovations in materials were very important for innovations in transportation. And of course, then in many different applications today, we find sandwich construction from aerospace to packaging, and our target is to reduce costs further by minimum amount of material used and by efficient processes. Also in space applications, the fairings, for example, are made with carbon fiber and aluminium honeycomb. Also these legs from reusable rockets are made with carbon fiber and honeycomb core. And Elon Musk is fan of honeycomb sandwich construction, and he says any super fast thing works with honeycomb sandwich construction and two skins. And if you look to the construction, sandwich construction, it's well known that we can save a lot of weight with sandwich construction by using an inner layer, which allows them to use much thinner skin materials from the same material, and results then in up to 80% cost saving, weight saving first of all, by saving the material. And if the material is structured from the same material, then it can be in the core 20 times lower in density. And that results finally then also in a cost saving. So you can save with sandwich construction as much cost as you can save weight, despite or if you have a production process which is very cost efficient. And especially with thermoplastic materials, the production cost is also dependent on how much material you process, because you have to heat the material, you have to cool down the material. So if you have a very a good construction method to make panel material with much less material, then you can save also energy and costs during production. And there are, of course, many different types of core materials which can be used. There's foam cores or cup-shaped or corrugated type of cores, and honeycomb construction. And if you look at the different materials, the corrugated cores provide a unidirectional support. They're very efficient in production, so you can produce them very cost efficiently, very fast. They're well used or well known for packaging applications, but the properties are not as good as, for example, with the honeycomb cores, because they don't provide support for the skin in both principal directions. And the support, the unidirectional support or the corrugated support can buckle very easy under compression loads. While in the honeycomb construction, you have cell walls which support each other and vertical cell walls, which leads to the best mechanical properties for a core material. And in the past, only the manufacturing was problematic. And this was due to The not continuous, the batch-wise production process of honeycomb cores. So this is the traditional method where layers are bonded together to a block, and then this block is expanded, and in the case of aerospace honeycomb cores, it's dipped into phenolic resin, cured in an oven, and then the honeycomb is sliced from this block. So it's a very labor-intensive, not very economical, and also not very ecological process due to this Nomex paper and the phenolic resin which needs to be used. The process is actually originating from a company in Halle, where we have our production location today. So this expanded paper honeycomb production process was invented 1901 for decorative applications, first in Halle. And today also thermoplastic materials are processed to honeycomb cores. Here are two techniques which use both a block. So first tubes are extruded or smaller blocks are extruded and joined to a big block, and then the honeycomb is again sliced from this block. So this is rather difficult to automate and leads to rather high production costs. So this, in principle, is this road via the block, and our production road is a continuous production which produces first a structured sheet, a continuous web, which is then folded up to create the honeycomb core. And this uses essentially the internal structure of aerospace honeycombs with the good mechanical properties and the low weight, and combines this with production principles from packaging industry. So very cost-efficient, automated production. And our process starts from a sheet, forms with rotational vacuum forming this pattern into the material, and then this material is folded up. So this is a patented technology and leads to minimum amount of material and minimum production costs. So essentially we start from extrusion, so from a granulate, have film extrusion, and then a direct rotational vacuum forming, and then folding up of this sheet to create the honeycomb core. So it's a continuous inline process with minimum amount of material and minimum production costs. Highly automated, and well, also the guys from Tesla, they say if you think of a line, you have to think of a highway. It should be maximum velocity down the highway, no start, stop, no city driving. So you want the highway, and we want the German highway, actually. So very efficient inline processes. So we have two companies. We produce the core material under ThermHex, and we have the company Econcore, where we integrate the core production directly inline to a panel production. So these two companies, one is in Belgium, started 2005, and that's in the capital of innovation. And in Halle, we started the production in 2010, and that's at the birthplace of honeycomb production technology. So this is our location in Halle, about 5,000 square meters, very close to the city because it's very environmental friendly, clean processing of thermoplastics. And we last year produced about 1 million square meters of honeycomb cores. So a very automated production, maximum production width 1.4 meter, standard is 1.2. We have very automated production quality control and maximum speed of more than 10 meters per minute. So with this we can produce a honeycomb core with very small cell sizes and in thicknesses from 3 to 30 millimeter. So we have special skin elements to bond the skin due to our production process, and this allows a very reliable core skin bond. Our customers are usually the composite industry, so in many different applications, caravan, generator covers for windmill, prefabricated bathrooms, truck sidewalls is a very big market, and of course automotive applications. In automotive, we supply material for door trim, for parcel shelves, and also for luggage floor. So for the luggage floor especially, or for automotive in general, the Organosandwich material is a material where we directly inline join UD cross-ply skins on our core. So we produce the core and directly have UD fiber reinforced skins on the core. And this material can then be further processed with injection molding or compression molding equipment by preheating and then very fast forming and finishing of the part, optional with injection overmolding. And that we have developed together with the Fraunhofer Institute in Halle, this further processing. And it allows to have the part at the edges then compacted in one step, to have different options to finish the part in one shot. Very cost efficient and very fast. So if you look at the material properties of such an Organosandwich, we see here a comparison between 2 mm steel and 3 mm aluminium and 4.5 mm UD cross-plied laminate of glass fiber polypropylene. So they have all about the same bending stiffness, and the steel has here about 16 kilogram. If you go to the right side, you see 16 kilogram per square meter, and aluminium and the composite are both about half, with 8 kilograms per square meter. And if you then look in the fourth position, we have the two skins, just 2 times half a millimeter glass fiber, which is about 2 kilogram, but of course very little bending stiffness with such a low thickness. But if you put these 2 times half a millimeter onto a sandwich core of 5 millimeter, then you get a 6 millimeter thick panel, which has then a weight of about 2 kilogram and has about the same bending stiffness than the other materials. So this shows with very little amount of materials you can reach a very good bending performance, and you can outperform many of the other materials. And in the last column, you see then the effect in bending stiffness of a thicker panel. If you go to 10 millimeter, then you have a much higher bending performance and only a very little increase in weight. And cost-wise, you can, these glass fiber composite skins, as well as our polypropylene honeycomb core, you can say about €4 per kilogram is a good price for a large volume. And if you add €4 per kilogram to this 2 kilograms per square meter, then you have about €8 per square meter where you can get a sandwich panel. And we think there are many applications in automotive which could benefit from these materials. So in underbody panels and door trim, also in battery housing or luggage floor and seat structures. We are in different projects involved to develop such materials for these applications. This is one example for a luggage floor from a Hyundai car, which is already in production and since several years now. And it has replaced a polyurethane glass fiber paper honeycomb part with a complete thermoplastic recyclable solution. The hinge you can see is directly in the material, so it can be pressed to form a hinge to fold up the luggage floor. And if you compare the different materials, above you have here the paper honeycomb polyurethane, which was the previous solution, which is based on paper, but with the polyurethane impregnation, it's not recyclable anymore. And our thermoplastic solution is complete polypropylene glass fiber and can be grinded and recycled. If you look at the different performance, this is the 3-point bending load. You see the first one was the part which they had to replace the polyurethane part with paper honeycomb and glass fiber, but this was not moisture resistant enough. Because if you have the paper honeycomb not impregnated with the polyurethane, then it's not moisture resistant, and they had problems with this. So our target was the column number 3, to replace the first column with a thermoplastic honeycomb and glass fiber mats. And there are paper honeycombs with polyurethane is the column number 2. And those can be replaced against glass fiber polypropylene UD tape sandwich, which is in the column number 4. And in 5, you see the last one is a recycled PET-based honeycomb with PET glass fiber skins. So this is was the maximum force, and this is bending stiffness. There you see also with a complete UD fiber, we can compete and can outperform the polyurethane paper honeycomb. And there was already recycled PET in one of the panels as a comparison. This is the next step for us. We are currently producing from polypropylene granulate, the polypropylene honeycomb, and then glass fiber polypropylene skins for these parts, and are in development of a honeycomb core based on recycled PET flakes from packaging grade, so not bottle grade, can be even from recycled bottles, which are then used in packaging first. So very low-cost flake material we can use because it doesn't need to be transparent. And we can process this to form the honeycomb core and then automotive parts. So this has a very low CO2 footprint, much lower than foam cores, and can be completely recycled. So this brings me to the conclusion that we have with our process a fast inline production process for the cores and the panels, which allow then a maximum cost saving. We have the excellent mechanical properties of a hexagonal honeycomb structure, which allows maximum weight reduction. And we have recycled material, a minimum amount of material, and recyclable material, which is maximum resource efficiency. And this goes very well together because we have, with a continuous production, a very cost-efficient way to produce those materials. We have, with the honeycomb sandwich, the weight reduction, and with thermoplastic composites, we have a very resource-efficient recyclable material. So with this, thank you very much.
Yeah, thank you for this detailed view on I think, a very, very interesting material. We have time for maybe 1 or 2 questions. There's one question. Please use the microphone because it's recorded.
Well, thank you very much. And my question is, how many recycling material you use in the existing production? How many will be in future? And how do you change the materials in a continuous process from virgin material to recycling material?
Yeah, we have currently in our polypropylene production, we use the edge trim and startup material that we can directly recycle because that's in-house recycling. We know exactly what type of materials we use. In the polypropylene production today, we don't use recycled material, other recycled material, because in polypropylene, the recycled stream is very difficult to get stable quality recycled material. That's with PET much easier. So with PET, we will only start with production from recycled material, and we are just starting now in Leuven to produce PET-based honeycombs, 100% from recycled PET.
I have a second question. Do you have the feeling that your customer asks more and more for recycling material? Really?
Yes, well, the big advantage from the recycled PET is it's also more cost efficient. Okay. So then both things are well aligned. It's cost efficient and recycled based. For polypropylene, it's difficult to find sufficient good recycled pure resources and to have a stable product quality at the end. But with recycled PET, we are very confident that this will be a very good product.
Thank you.
You're welcome.
So if there are more questions, they have a booth down at the exhibition.
Yes.
So I think he's more than looking forward to any questions and discussion with you. So let's thank our speaker again.
Thank you. Thank you.